All right. Okay, so the plan for today is to finish this ray tracing geometry slides, which are basically to solve two things. First, to generate our rays from our camera focal point to the image pixels. After we have those rays, the next thing will be to intersect those rays with the objects. So we are going to see uh, ray triangle and ray sphere intersection methods or mathematics of it, and also how we generate our rays given an arbitrary camera position, an arbitrary gaze, an arbitrary location of the image plane. All right, so setting up the image plane and its distance to the camera is really important to have like different field of views. If you want to zoom in a certain, you can have zoom in, zoom out effects, and we are going to talk about all these today. All right, and I'm going to show you an example code that I had written a couple of years ago, which is really simple and implements the geometry part and part of the shading part too, actually. But you're going to see it's very simple. So writing a pure ray tracing code with pure C, no libraries at all, is very easy, and it will help you to generate images of some virtual world. So this will be your first program. You may try it out yourself, or I may share this code with you that I'm going to show you. It's very simple. You're going to see. All right, so let's start and let's first discuss what's going on here. Let me put it to the left-hand side. The chat window may remain on the right-hand side. Okay, so yeah, here one important property, the element of ray tracing, as I said, is the camera. A camera and image plane actually together form the camera itself. I mean, on the slides, the camera is just shown to have the location of the focal point where the rays originate or light rays collect. You may look at this from two different perspectives, and so either light rays collect at this focal point E, or it's the position of your eye or position of your camera. It's the central point of your camera. You can think about it like that. And also it comes with, in order to determine what a camera is, its extrinsic properties, where it is in the world, its position is important, right? I mean, when you're taking a picture, the position of the camera is important. Another thing is its orientation. Okay, so the orientation, we give it by these three vectors, which are sometimes called the gaze vector. Here, the gaze vector is not shown on this figure. So if I get this pen, so this is the gaze vector. So if these are the this basically defines a local coordinate reference frame around our eye, which is like the center of our local coordinate system. It's the origin of our local camera coordinate system. We can sometimes call this viewing coordinate system. So it's, as I said, it's local because this point E can be in an arbitrary location with respect to the world coordinate system. So this is, if this is the world, if the world coordinate system is somewhere here, this E can be in an arbitrary location, and these axes may be oriented in arbitrary direction depending on where you want your camera, your gaze to look at. So gaze is the looking direction of your camera, okay? And it is by default, by convention, it's the minus z axis of your local coordinate system, or minus w vector here. And u is the positive x-axis of the camera. V is the positive y-axis of the camera coordinate system, and they're all orthogonal to each other. Okay, so there are 90 degrees in between each of these three vectors. They form a coordinate system, and they are usually given to us in unit vectors. If not, we have to normalize them so that they become unit vectors. In my code, I'm going to show you what kind of an input we may be given. Sometimes the gaze is given, but the up vector is given in such a way that it shows, for example, maybe what I'm saying is this. Sometimes, let me use some, so this may be the gaze, okay? Now I'm going to use a second pen here. So up vector, actually, as you can see, it should be orthogonal. If this is the gaze, if this is the camera, the up vector should always be orthogonal to the gaze vector. So when the gaze vector is pointing downwards, as you can see, up vector moves along with it. Sometimes we give the up vector, I mean, instead of giving, it may be difficult to directly give the up vector relative to the gaze vector. If you want to look down like this, okay, instead of giving the up vector also pointed down, the up vector is, the up vector also tells you whether this camera is straight up like this or tilted, okay, because if the up vector is a little bit, it has x component, it's going to move left and right. Sometimes we give the up vector regardless of the gaze vector, okay, if the gaze vector is this, we give the up vector not like this, orthogonal as input, but we give the up vector sometimes like this. Just in order to say that it's not tilted, we just give up vector to be the value of 0, 1, 0, although the gaze vector is this. So that's an invalid up vector, as you can see, so which has to be corrected. So in OpenGL, for example, this correction is done automatically. So I'm going to show you also sometimes up vector just shows our relative tilt to left and right. Therefore, in order to say that we are not tilted left and right, we give the up vector as 0, 1, 0, which is not the v vector, correct v vector. It has to be corrected. All right, because if your gaze is a little bit down, I mean, if your gaze is straight ahead, okay, no matter what direction it has, it may have some x and z components, okay, you may be looking, and if you're looking straight ahead, whether you're looking this way or that way, it doesn't matter. Up vector is always 0, 1, 0. But if you start to look up or look down a little bit, up vector is not going to be 0, 1, 0 anymore, okay, it's not tilted. As you can see, if you look at from this side, when I tilt it, you don't see actually the up vectors y component is like it's not tilted left and right like this, but it's tilted forward. Okay, so we have to do this correction, and I'm going to show you how we do that in the code that I have written. Okay, so basically this is the local coordinate system of the camera that is defined, but when we say image plane actually is part of the camera in real life. A camera is not just a focal point. A camera like this comes with a sensor, and its sensor is built in the camera, and that's the image plane we're talking about. The image plane is the sensor array where the light photons are collected. So this system actually is the camera. But image plane could be independently, so it's like an intrinsic parameter of the camera by changing, for example, the distance. Look at this distance. By changing this distance, you're changing some internal parameter of the camera. These are like, sometimes in computer vision, you will have these terminologies, extrinsic parameters, in which outside parameters, you change the camera's location, orientation, these are outside parameters. But intrinsic parameters, the internal parameters of the camera, like this distance, the length of the size of the image plane, things like that, can also be changeable. Now, here there are really important parameters that we're going to talk about. The resolution. Okay, the resolution tells us in this rectangle. First of all, let's define this rectangle. The image plane itself, the plane is unbounded, right? A plane is in 3 dimensions. 2D plane is something that is unbounded. It goes in every direction, this way, that way. So this plane that we are seeing here, it's if you write this plane equation, it's unbounded actually. It will contain all the points on the plane. I mean, if you write the plane equation like this, ax plus by plus cz plus d is equal to 0. That's the plane equation in 3 dimensions, in which these a, b, c, d are constants which determine where this plane is. It's one of them. A, b, c actually determines the normal vector of the plane where it is looking at its orientation. And D, actually, in this orientation, there are infinitely many planes. If you stack them right one after another, it will be like this. So there are infinitely many such planes. D is the parameter that fixes it to this plane. So anyway, so what I'm saying is plane actually is something infinite. So which sometimes, therefore, we call this image window. An image window is a region, a rectangular region on the image plane. All right. So, but I mean, we use this. Sometimes we abuse terminology. I mean, when we say image plane, most of the time we just indicate this rectangle. We don't actually refer to this infinite plane. Image plane. I mean, sometimes by mistake we can just say this is the image plane. All right, so that's okay. But there are four parameters. I mean, this L, R, B, and T are really important parameters. It determines the size of the plane in the world coordinate system. So what is the size of our sensor array? What is its dimensions? And the dimensions are given in units with respect to this U and V, which is the same, our measuring unit in the world coordinate system. Okay, for example, L, B, R, and T are scalars. Okay, they're not vectors. L is the signed distance from the center of this image plane to the left boundary. Okay, L is this parameter. L is used to tell us the left boundary of the image window. Okay, and it's given as a scalar. It's the distance from this E, which is, I mean, if it's orthogonal like this, so it's the distance from the center of the image plane to the left boundary of the image. And most of the time, for example, it's given like -2, okay? And R, not most of the time, in example. So L is -2, R is 2. When I say something like this, -2, as you can see, -2 cannot be a distance itself, but as I said, it's a signed distance. It means that from here to here, there are 2 world units that the image occupies. And from the center to the right, the image occupies 2 other units. So the width of this image window is 4 units in total. Okay, it's 4 units. And B and T are similarly. For example, if it's -1 and this is 1, okay, it's the signed distance from the center towards the bottom. So this becomes a rectangular image which is 4 by 2. It becomes a 4 by 2 image in terms of size, width, in world units. This doesn't mean that its resolution is 4 by 2. Okay, it's the size of the image window, dimensions of the sensor array in the real world, 4 by 2. Now, we may have in this 4 by 2 unit area, I mean in this 4 by 2 rectangle, we may have millions of pixels. Okay, if you want billions of pixels, because that number of pixels is determined by another pair of parameters, the resolution, nx and ny. And here, and nx and ny are 2 integers, which tells us how many pixels we have in a column. Okay, nx is how many pixels you have in a column, and ny is how many pixels you have. Sorry, not in a column. When I say in a column, I'm showing a row, and I'm saying how many pixels you have in a column. So nx tells you. So if you look at the coordinates of this, so nx is your which column you are in. Okay, basically it tells you how many pixels in a row. Okay, so as I said, it's a 4. So when it's an nx by, if its resolution is going to be nx by ny, and nx is the number of pixels in a row. Okay, it's the size of a row. And ny is the number of pixels in a column. It's height. All right, so we are going to be given these things, and this one, nx minus 1 and my minus 1, or I mean, if the coordinate is like this, if you look at the coordinates, that's the x coordinate. This is the x coordinate on the image plane in terms of integers, so which is in this direction. Okay, so the x coordinate of the image plane is this direction, y coordinate of the image plane is this direction. It tells you, and our center on the image plane, so the image itself has a different coordinate system, which is 2D, a 2D coordinate. Our pixels also live in a 2D coordinate system, and by convention, we again have an origin here. The top left pixel is named 0, 0, okay, is index 0, 0, okay, and then this one is going to be nx, so this one here is going to be nx minus 1. The coordinate of here is nx minus 1, 0, okay. The coordinate of this pixel is nx minus 1, 0, and the coordinate of this pixel is nx minus 1 and minus 1. So it may be confusing a little bit if you think about these indices as array indices, because in arrays we usually use the first element to indicate the row, right? I mean, I may even have confused myself here whether because I was talking about rows and columns, and I was actually thinking that nx, I mean, this first, if this is like an array, two-dimensional array, the first element shows the row number, right? Therefore, this should be the y-axis actually, not the x-axis, if it's the row number. We are going to see that soon, all right? I mean, in the next slide, the way we compute the coordinates of this, it will be clear whether this is the coordinate, I mean, whether this, so the question is, the top right pixel, is it nx minus 1, 0, or 0 ny minus 1? Okay, either one of those. So I mean, if it will be 0 ny minus 1 if we are using the coordinate as if we are indexing arrays. The first index indicate the row, the second index indicate the column. But if you're using the convention of xy coordinates, the xy coordinates convention, the x coordinate is given by the first element. So this should be nx minus 1 then, and the y coordinate still is 0 if this is the y coordinate, okay? I'm confused between these two things, but as I said, it will be clear. Whatever convention we use, I mean, if you write your code consistent within how you understood this, it will not matter at all right? But in order to be consistent with the slides, we need to just distinguish between these two. What nx and ny in terms of image coordinates? Are we using these image coordinates as if we're indexing an array, or are we using the image coordinates as if we are on the xy coordinate system, in which x is this and y is this, and local coordinate system of the image plane in integer coordinates? Okay, so but you understood the parameters. The important parameters here are the size of the image window, which are given in scalars like -2, +2, -1, +1 is assigned distances, and we are given the resolution of the image, nx and y, which I know nx is the number of columns in a row, and ny is I mean, this is the width of the image and the height of the image, so it's given by width times height. And we are also given the distance of the image plane from the eye point. That distance determines actually our perspective field of view. If the distance is closer to the camera, we are going to have a higher field of view. For example, the field of view can be determined. The vertical field of view, for example, if you draw these two line segments from to the two corners, this angle is your vertical field of view. And if you draw these two lines to the top and the bottom, okay, so this angle and this angle, so this angle is the vertical angle, this angle, sorry, yeah, this is your vertical field of view, this is your horizontal field of view. Your horizontal field of view is this, your vertical field of view is this, and they can be different. The angles of your horizontal field of view and vertical field of view may be different depending on the sizes, the dimensions of your image window. Any questions up to now? Okay, I hope it's clear. So we are going to be seeing examples, and we will be using these values extensively to determine the coordinate of the center of a pixel. For example, let me ask you something first. This is the 0, 0 pixel, as you can see. The 0, 0 pixel, its location, I mean, this lower, the coordinate of the top corner of the image window is not the same as the coordinate of the top pixel. Okay, the pixel coordinates actually are at the center of the pixels. This top left corner of the image has a different coordinate, and the difference between these coordinates actually is about how, not about exactly, I mean, if in this unit in u direction, it's if you go in the u direction, half pixel width in the u direction from the top left of the image window, you will get to these coordinates. The difference will be half pixel width. Okay, so if what is the pixel width here? What is if I do, for example, r plus l? Okay, so what is r plus l here? If l is given as no, sorry, not r plus l. I need to do r minus l. Yeah, sorry about that. Let me erase this one. What is r minus l? R minus l is the width of this rectangle, right? If you divide it by nx, what do you get? You get the width of a pixel. So if somebody asks you how large are your pixels, what is the size of a pixel? It in real life, for example, on a monitor. How do you determine the size of a pixel on a monitor? You need to know the resolution, nx and ny. You also measure the width of your monitor, how long it is. It's 80 centimeters, 50 centimeters. So you divide that 50 centimeters by number of pixels to get your pixel width. So this is our pixel width. Okay, if you divide this by 2 again, okay, if you multiply it with 0.5, that will be your half pixel width. Okay, so your half pixel width will be this value. Oh no, we don't define an epsilon value. Oh, okay. If the I mean, if you're dealing with floating point numbers, I mean, we will not actually go that small enough. We will not go to the our pixel widths will not be as small as 10 to the minus 6. All right, it will be much larger than that. For example, if you can put 1000 pixels here, for example, if your image window width is 4, your pixel width, if you want to put 1000 pixels here, it's still going to be a 4 divided by 1000, which is still larger than 0.0001, right? If it was 1 divided by, so it's going to be 0.004. Okay, it's still the floating point operations. I mean, the accuracy of the floating point precision is not going to affect our computations. We will still be able to compute this at this precision. Yeah. So I mean, even if you have, I mean, 10,000 pixels, 10,000 pixels is a lot, right? I mean, imagine a 10,000 by 10,000 window. It's 100 megapixels image, right? 100 megapixels is quite large. So even in that case, we are still much. I mean, we can still play with the floating point precision. If you want double precision, will be sufficient to indicate your pixels. So the difference between the x coordinates here will be around a pixel width, and we will be playing with those pixel widths. All right, let's continue. And the image here is typically, it's not necessarily so, but the image is typically centered. I mean, the gaze pierces through the center of the image most of the time, but sometimes it's possible to move have the r larger than absolute value of L, in which the image is going to be like to the left. R and L are sign distances. So with the help of with the addition of the u vector, for example, if you say r times u will tell you how long you have to go in the u direction to hit the right boundary of the plane. So r and L are scalars. Okay, but if you multiply them with u, it will tell you in the x direction, in the horizontal direction of the, I mean, u basically tells you the direction of the rows of your image. Okay, so if you multiply r with u, it will tell you you have to go this in this direction, this many units until you hit the right boundary. Okay, R and L will be their sign distances that we will use them to get to the end of the image. Yeah, there it says they're like LRBTR with coordinates are with respect to the camera coordinate system. They're not actually coordinates, as I said. They are L or and you may consider that as at y is equal to x is equal to -2 line. You can consider L as an x is equal to -2 line. But I mean, just it's better to think of them just like sign distances, which tells us how many units we need to go in the U direction to get to the left and right boundaries of the image. And yeah, so that's very important, the image plane. And with the examples, I think it will be clear after we talk about how we compute the pixel coordinate given any ij. And the other important elements in our ray tracing are objects, and many objects can be just composed of triangles. So if you have a way to intersect your rays with triangles, they may be very tiny triangles, but still they are triangles. You will be able to actually, yeah, you can see the cat right there if you, in my window, so they're here. Okay, so yeah, so whenever I start talking about objects, cats wanders into my room. Yeah, an object of affection, as you said earlier. Anyway, so here, as I said, any object can be made out of triangles, small triangular meshes. And knowing our primitive objects, if you know how to intersect your rays with spheres and with triangles, that will be sufficient for now. Okay, for a basic ray tracing. I mean, even in advanced cases. So even spheres, we don't need them as mathematical objects, but it's easy to intersect triangles with spheres. We can even represent spheres as triangular meshes. All right. So some objects will contain many triangles, some less. And the objects will also have different materials. For example, you see here 4 spheres, each of which is like different. This one is really matte, the purple one. It has no specular reflection on it. What it means is that in real life, this means that your looking direction to the sphere, the purple one, does not matter. The light rays coming on to the sphere is reflected off in every direction in equal amount. All right. So this is what it means to be matte. I mean, but if you're shiny like this, light directions hitting on this are reflecting off so light is coming here, it's reflecting in a particular direction. So it acts itself like an image plane. So it's like a camera that we see some photographs of the scene around it. But here, light rays coming here are reflected off in every direction equally. Like, so this is called diffuse component of a material, and this is called the specular component. This is how we are going to model materials. This has some shininess component, we can see, but it's blurry, as you can see. This one is not as reflective as the other one, but it's not as matte as this other one. So there's some shininess to this green sphere. Okay, so this one also has a lot of reflections on it, but it's not white like this. It also has a component. It also has a diffuse component, like reddish component, and it also reflects the light that is coming to it. Okay, actually there's a name to these things. So this is high gloss, diffuse, mirrored, and semi-gloss. So these are some material names. I didn't know this high gloss, semi-gloss terminology. For me, we are going to model the material, the light reflecting of objects using 3 components in our simple model, and we are going to talk about those next week. Okay, and light sources can be various in the scene. We are going to start with very simple light source, which is positional and emitting light in every direction. But we can have directional light sources in which the light position is actually at the infinity. For example, it will be easier to model the sun as a directional light source, because I mean, the difference is that in a directional light source, the light direction is constant no matter where the object is. For example, the sun is very far away from Earth, right? Therefore, wherever you are, I mean, whether I mean, in an image, when you take a photograph, the light rays are coming in equal vector directions to object in your scene. It's like the sun is at an infinity, so all the objects in your scene are receiving light in the same direction vector. That's the directional light. But if you in a dark room, if you have a light source in the middle of the room, not all the objects are going to be illuminated from the same side. It will be important to position the objects. For example, if the object is to the left of the light source, it will receive light this way, but an object that is to the right of this light source, it will receive light in a different direction. Okay, so these direction vectors will be different if you have a positional light source. So we will be considering positional light sources in our ray tracing algorithm. Also, there is the ambient light, actually, which means that light is not just coming from the light sources. The objects around us, they also, the light that is bouncing off them is also like a light source. Okay, so and therefore there is ambient light, the light that is everywhere. Ambient means being everywhere. All right, so there is, without the actual light source, we also have light bouncing off everywhere in the scene. And in reality, in order to model these light bouncing off everywhere, there are algorithms which is called global illumination, which try to accumulate these light coming off walls in like an iterative manner. It integrates the light in different iterations, but they're really costly, these global illumination algorithms like radiosity. If you wonder about those, you can look up this method, radiosity. It's basically it's a really advanced algorithm. You're not going to see that algorithm here, but it takes into account this ambient light collected from the surfaces of other objects. But in our model, we will simplify this ambient light computation by just assuming there is a default amount of light regardless of whether you see the light source or not. I mean, this will tell us, for example, the ambient light basically tells you that even if you're in shadow, are you totally dark? I mean, imagine there's a light source in the room, but there's an object that occludes another object. So the other object should be in shadow, right? But in reality, because of the lights that are bouncing, light rays bouncing off the walls, you will still be able to see the other object that is occluded by this. It's not going to be totally black because of the ambient component. So you can consider the ambient component as this default light in the environment that is apparent regardless of the light source's direction. Okay, so we will do that. Now let's get back to our first mathematical computation. How do we compute the ray that passes through a pixel's center? And by the way, you're going to have a recitation given by one of your teaching assistants, Bilgin, tomorrow at 5:40 if I remember correctly. But just check the OT class announcement and the cow announcement, and he's going to be talking about these vector operations, some mathematics about this, how to represent lines, how to do some vector algebra, things like that. Yeah, reflective objects also, they are reflecting the light source, but the light is not as powerful as it's originally from a reflective object. But in ray tracing, we will actually assume that the reflected light, we are going to collect light coming from reflective objects as well. So they will be like light source. We will be following the ray, and if it is a reflective object, for example, but actually you're right. I mean, it should affect the ambient component, but we will ignore that. We will not, in our ray tracing algorithm, we will not treat them as light sources. Okay. The reflective objects, we will just treat them as if they're collecting light rays coming to them, okay? But I mean, and they reflect off the light rays to us, to the image plane, but we will not use them as a source of light, photons for the other objects. So that's a really tiny distinction, okay? What I'm saying is that the light rays coming off the reflective object to the image plane, the light rays that are reflected to the image plane, will be our focus. We will be using them to say that, oh, okay, this reflective object receives the position of the other, I mean, gets some light from the other object, and it's reflected as is to us, okay? But it will, by itself, we will not treat them as light sources, although they can be, right? I mean, you imagine the light is also an object. The light rays that are coming off the reflected object at that point acts like another positional light source, all right? But we will not do that. We will not consider them as a light source on their own. But that's a good point. So there are lots of real life physics that needs to be considered. But when we are developing these algorithms, the way we develop them, we need to make lots of simplifications, lots of abstractions, assumptions, so that it's doable in real time. Or I mean, we want to do it efficiently. But in the ray tracing algorithm that I'm going to describe in this course, we are not going to use reflective objects as light sources. But as I said, we will be using the light rays reflecting off them towards the camera to get the color at that particular point. So a ray, basically, in parametric line equation, it's very simple, okay? I mean, ray equations are really simple. So there's a single parameter t, which we parameterize the line. For example, starting at O, this is the origin, and going in direction d, this is the d vector, okay? So d vector is this vector, and this is a point, okay? O here, both of them are both of them are three-dimensional vectors. O is a three-dimensional vector, but we use its semantics as we use the semantics of O as the position to indicate a point in space. D here is also a three-dimensional vector. Okay, it has XYZ components. O has also XYZ components, but the way we treat O is as a position, and we treat D as a direction with a magnitude. All right, D is the direction vector, and as you can see, this is just vector algebra, adding a vector to another vector which is scaled. We scale this vector by t. T is a scalar parameter which tells you where you are currently on this ray. When t is equal to 0, if you give 0 to t, where are we? We are at the origin, okay? So here t is equal to 0. If we give 1 to t, where are we on the line? At the tip of the arrow. Okay, so when t is equal to, yeah, exactly. When t is equal to 1, we are going to be at the front of this arrow. So, and t could be from minus infinity to plus infinity. It will be this line equation. All right. Now, here's the thing. Let's get back to this image, okay, with lots of drawings on it. So let me write a ray equation, which I'm going to call, for example, G, because it's the gaze line. GT is equal to E plus minus W T. Okay. Actually, let me multiply minus W with distance as well, because minus W is unit vector. Okay, if I multiply it also with distance. Look at this. What did I do? Now, here, t is here. I had to put it into the middle because it actually should appear at the end. But so minus w times distance will be this vector. Okay, so look at this vector, which is here and start. This is the direction, minus w direction. I scaled minus w, which was unit vector, with the given distance. So minus w times distance is this large vector. All right. Now look at the line equation I just formed. E plus minus wt distance. What does this mean? It's this line. So when t is equal to 0, where am I? I'm at the I point. When t is equal to 1, where am I? I'm actually at the center of my image. Okay, so when you give 1 to t, this basically tells you this direction, the size of this vector tells you with every one of those vectors where are you. Okay, so this when t is equal to 1, you just add minus w times distance to this vector. From here you add this, you go in this direction 1 unit, just with one vector, you will be here. Okay, so with this ray equation, what I can do, for example, is intersect this with a sphere in front of the image. When I intersect this, the intersection result will be the t value. At t is equal to what I'm intersecting, if at all, if this ray intersects at all with the sphere. So we are going to see this, we are going to use this ray equation and intersect it with the sphere equation to find ourselves some t values. Most of the time you may get 2 t values because a ray intersecting with a sphere, if it pierces through a sphere, there will be 2 intersection points. And the intersection points will be identified along the line by this parameter t. Okay, so any line, when we have a ray like this, any point on the ray can be identified uniquely by this parameter t. This line, although it's a three-dimensional line, okay, so this is ox, oy, oz, dx, dy, dz, it's a three-dimensional line. But even a three-dimensional line is a one-dimensional object in 3D. Why I say it's a one-dimensional object? Because if you were a person living on that line, your address would be just one scalar, t. Okay, so t is therefore any object that is living on this line is living in a one-dimensional world. So if the universe of everything points that are living on this line think that's their whole universe, they are living in a one-dimensional universe. Okay, the line is a one-dimensional object, even in a three-dimensional world. All right, so this is therefore there's a single parameter, and we will be using this parameter quite a lot to know where we are currently on the line. For example, where the intersection is. Let me ask you some questions. When we intersect a ray like this with a sphere, and the smallest, and the two t's happen to be 0.2 and 0.4. What does this mean? Any ideas? Where did the intersection occur? You can write in the chat box. Exactly. I mean, the sphere is inside the camera. It cannot. I mean, we shouldn't be able to see this object, right? I mean, we can only see objects. I mean, for our camera model, if this is like a camera with an image plane in front, we should be able to see only objects that are in front. So we are interested in intersections in which t is greater than or equal to 1.0. Okay. If t is less than 1.0, it means that that's an object. I mean, somehow our camera got into a sphere, and there's a sphere inside the camera. We shouldn't be able to see that. Okay, so there's a sphere inside our camera. We don't want to display that. We want to display on the image plane only things that are in the front. Just think about this whole thing. as our camera. Okay, this is like a solid box. There shouldn't be anything inside it. But since we don't have collision test in our virtual world, there may happen to be a sphere, a small sphere of radius 0.1 maybe inside inside it. So, but we should ignore that. We shouldn't be displaying that. Also, when, for example, what happens when t is less than 0? The intersection occurs and t is less than 0. It means that there's a sphere that is behind the camera. Again, we shouldn't see that, right? Because when we form these line equations, it will be an infinite line. When we intersect it with the objects in our scene, it will intersect with certain things that are behind us. So things that are behind us, we should not project them onto our image plane. But actually, if you do that, that may be an interesting effect, right? I mean, if you just project everything, whether they're behind or front, on the image plane, you may get an interesting view. Like you can see both the front and the back of your. It's like you have eyes in the back as well. Okay, but that would be interesting. But we don't want to do that in regular ray tracing. Our goal is just to display objects in the front. Therefore, we are interested in intersections in which t is greater than 0. So this parameter t is really important. We will be using it to identify shadows by looking at the value of t or other things. Okay, so the basic algorithm of ray tracing is really simple. For each pixel on that image plane, we are going to first compute the viewing ray that starts from the point E and passes through the center of the pixel. So we have 2 points, point E, the eye, the focal point, and the center of a pixel generate that ray. And each ray is going to have a different equation. When we have 1 million pixels, we will have 1 million different ray equations. One of the points of the ray, the common point of all those rays is E, but the second endpoint are pixel centers, which may be different. And after we compute the ray, we intersect this ray one by one with all of the objects in our scene and find the first object hit by the ray. The first object is important because we'll assume none of the objects are transparent. If all of the objects are opaque, objects that are behind are going to be hidden by an object that is in front. Okay, so for example, right now you can see this hand, but there's another hand behind it, so you cannot see it. So from your point of view in the camera, this is the first, the rays coming from the camera is hitting this hand first. In other words, its t value, the intersection's t value is smaller for this hand and larger for this hand. Therefore, you see the hand in the front. So we are going to find the first object hit by the ray. It's very simple, actually. Just keep track of the minimum t. Keep track of the minimum t, and that's it. And after we find which object it is, we are going to note its properties as well, not only the t. So it's whether it's a sphere, whether it's a triangle, and whether the material is shiny, matte. So which object we hit and its material properties will be recorded. And with that, we will be able to compute a surface normal, and we are going to compute a color based on the object that we hit, based on the position of the light with respect to that object that we hit, and compute the light rays, the color, and set the pixel color to that computed color. That's it. It's a very simple algorithm, and I'm going to show you the code for this in the second hour. Now, it's time for a break now. Let's have a 10-minute break, not 15 minutes, okay? Let's have a 10-minute break, and after the break, I'm going to show you the equations to compute the eye rays, okay? Okay, let's have the break, and I will have to finish early today at 11:20 because I will have to be chairing a session in a conference, online conference. So just after this class ends, the session starts at 11:30, so I will have to finish early today. All right, but let's have a 10-minute break. So I've been talking a lot. So at 10:40, we will meet again in 10 minutes, and I'm going to show how the equations to compute the ray equation for an arbitrary pixel in the middle of our image. All right, see you all in 10 minutes.